My name is Tommaso Menara, and I am a PhD candidate at the University of California, Riverside. In this video, I'm going to present my work on the analysis and control of collective dynamics in brain networks of oscillators. Synchronization phenomena are ubiquitous in the brain, and examples include large-scale integration of information, the storage and retrieval of new memories, motor coordination, and even circadian rhythms. In disease instead, synchronization can be used as a biomarker. In fact, cognitive decline has been linked to reduced synchronization in certain regions. In epilepsy, increased synchronization is thought to cause seizures. And finally, neurological damage causes abnormal synchronization. Therefore, the characterization and ultimately the control of synchronization in the brain are of paramount importance. But how can we do that? In our work, we exploit the recent terrific advances in neuroimaging, specifically in diffusion tractography, that tells us if and how different brain regions are interconnected. And by combining this connectivity information with brain parcellation, we obtain a network representation of the brain. In this network, nodes represent brain regions, and edges axonal bundles. In order to reproduce neural activity, we make use of Kuramoto oscillators, which have been shown to faithfully reproduce empirical data. To sum up, the oscillators' phase trajectories represent neural activity, and we are left with studying synchronization in networks of coupled oscillators. Activity recordings have shown that different groups of brain regions tend to synchronize together. Mathematically, we can represent this with the cluster synchronization manifold, which is the collection of all phase trajectories in which θ I equals θ j for all I and j belonging to the same cluster. In our work, we have exploited the natural frequencies and the coupling strengths in the Kuramoto dynamics to derive conditions for the invariance and for the stability of the cluster synchronization manifold. Building upon these conditions, we have designed minimally invasive and localized controls that allow us to recover a desired cluster synchronization pattern from a damaged brain network. As a proof of concept, we have taken a publicly available anatomical brain network and applied minimally invasive structural and frequency corrections to obtain cluster synchronization of 3 large groups of regions. To wrap up, hopefully I have convinced you that synchronization phenomena are ubiquitous in the brain. In this work, we have provided conditions for cluster synchronization in brain networks of oscillators. Finally, we have designed an optimal control framework to achieve cluster synchronization in networks with neurological damage. Before concluding, I would like to thank my dear collaborators Giacomo, Danny, and Fabio. And a special thank you goes to all the sponsors for supporting this video competition.